Earlier we saw what logarithms were for, in that the logarithms are really inverse functions of exponential functions. So if f of x is equal to the exponential function b to the x, then the inverse function, f inverse of x, is log base b to the x. Another way to write that is if we get rid of the f of x notation and suppose we just have given b to the y is equal to x. This implies that log base b of x is equal to y. So we saw that it's extremely important to be able to convert back and forth between these two expressions, the exponential expression and the logarithmic expression. An example that we saw in class was if you have 2 to the 5th equals 32, then log base 2 of 32 is equal to 5. So again, being able to write it in both exponential form or logarithmic form. We also saw on this example that there's another way to write the relationship between these three numbers. In that, we could also say that the 5th root of 32 is equal to 2. So we've got each of the three numbers isolated differently. One in the exponent is isolated using the log expression. The base is isolated in the radical expression. And the number, the 32, is isolated in the exponential expression. So three ways to write the relationship of those numbers. In example 6, we've got to graph the exponential function 2 to the x, and we'll plot several points, including the horizontal asymptote, and we'll find the inverse, f of inverse of x, by plotting more points. Remember, we just have to switch the x's and y's around the coordinates in order to get the inverse. So let's start by graphing what 2 to the x, that doubling function, looks like. So we'll plot some points. 0, 1 is on our 2 to the x function. We've got 1, 2, and we've got 2, 4 on there, and we can go backwards also. We can go -1 would be a half, and we've got our exponential function here. We can also put in the asymptote. The horizontal asymptote is the x-axis there. Now, to do the inverse, let's just take each of these 4 points and switch the x's and y's. So that means I'm going to have a point 1/2, -1 on my inverse function. We'll also have 1, 0 on the inverse. 2, 1 is on the inverse, and 4, 2 is on the inverse. And here's what our inverse function looks like. That would be log base 2. So this is the log base 2 of x function, and our original function was just 2 to the x. And we can also see that the vertical axis, the y-axis, is now also an asymptote to our log function. So what that really says is for our log, we can only put in positive values. So if we write down the domain and range, oh, and we can also see that we've got this symmetry of the inverse functions going on around that y equals x line. But if we take a look at the domain and range of the exponential function, we can see that the domain is from -infinity to infinity, and the range is 0 to infinity, so from not quite touching the horizontal axis up to positive infinity, which means for our inverse, for our log function, that domain and range is switched. So the domain now is from 0 to infinity, and the range is -infinity to infinity. So when we start graphing different types of log functions, whether they're shifted left and right, up and down, or scaled, we have to keep in mind what the domain of those functions are. So for example, let's say we wanted to graph f of x equals log of x minus 3 plus 2. So the domain this time is 3 to infinity, because we can see that you can't put in 3 into here. That would give you log of 0, which is not possible because log, it's just not defined. So anything greater than 3 is what we can substitute in for x. So our domain is 3 to infinity. Also, it looks like this graph is shifted up 2. So we might want to keep track of this nice number right here where the log function crosses 1, 0. That's kind of the nice point, similar to the nice point on your exponential of 0, 1 here. So to graph it, let's draw our line. Our asymptote is actually at x equals 3, our vertical asymptote. And that point, that 0, or that point 1, 0 over 1, 0 would have to be shifted up 2. So we're up 2 here. So that really gives us the point 4, 2 on this function. Now, most calculators do have two log functions on them, and those are the common log and the natural log. So the common log, since we count in base 10, that's how we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we use base 10 for our logarithm, that's called the common log, and the shorthand, rather than writing the subscript 10 on it, the shorthand for the common log is just log of x. So log of x is the common log. Also, if we use the natural number e as the base, that would be called the natural logarithm, or log base e. But again, that's simplified to ln x. It looks like it should be NL for natural log, but it's either Latin or French, I forget. It's logarithm naturalis, so that's where the ln comes from. And as I just mentioned, we do have these on our calculator, in that on the TI, they're on the very far left, log and ln there. And notice that those are also paired up with their inverse functions. The log function has 10 to the x, which is the exponential function with base 10, and the ln is paired up with e to the x, the natural exponential function. On the numworks, we have ln and log right in here. They're not paired up. We have the e to the x as a separate button, and then 10 to the x is also a separate button.